Mic test. Hello, and welcome to Object Recognition and Scene Understanding 2. I'm Michael Mayer, one of the session co-chairs, together with Subransu Maji. And our first talk will be on 3D RCNNs. The authors are Abhijit Kundu, Yin Lee, and James Ray, and Abhijit will be speaking.
Thanks, Michael. Good morning, everyone. So I'm Abhijit. So today we're going to talk about 3D RCNN. So this is a joint work with Yin and Jim Ray while we were still at Georgia Tech. So almost 150 years back, Helmers described perception as the best guess of what is in the world given our current sensory input and the prior experience. Now to describe what is in the world, we need a representation. So what should this representation be? So typically, most of the scene representations are always in 2D, starting from like 2D object detection boxes, or like a 2D instant segmentation mark, or even for body, we have 2D key points or body part segmentation. However, all these representations are fine, but they are not really that useful for a lot of real-world applications. For example, if you want your robot to navigate in 3D, you need a 3D representation. And these 2D representations are often not sufficient. So the goal of our work is to get a 3D representation of the scene. So our problem statement is like this. Given an image, let's get the 3D shape and pose of each and every object instances in that image, right? So now, if you can get this kind of representation out of the image, this is going to be much more useful for a lot of different applications. Now, if you really want to get back like a 2D representation, like let's say you want an instant segmentation out of it, you can just simply render it and get an instant segmentation, right? So all this comes free, right? If you want, you can get a depth map also out of it. So how do we get a 3D output from a 2D image, right? So in this work, we will be presenting our network called 3D RCNN. So the architecture is based on the faster RCNN meta architecture. So given the image, we have feature extractor. Then we do, on top of each region proposal, we will be doing ROI pooling. And on top of this ROI pooled features, we will be estimating 3D shape and 3D pose, right? Now, there are a lot of different questions now. Like, how do you even represent 3D shape? Or what should be the learning target for pose? Then there are also, another important question is, how do we obtain 3D equivariance, right? Which is important for this kind of task. Then another big question is, how do we train this network? Normally, it is very hard to get ground truth 3D data. So can we actually exploit 2D ground truth data for training this task? So throughout this talk, I'm going to answer these questions. So for shape, what we do is that we learn a low-dimensional shape representation. So we learn this class-specific, right? And for rigid objects, we do PCA, and for articulated objects like person, we use this SMPL model from Loper et al. So now the task of estimating shape is basically predicting this low-dimensional parameters of the shape instance. So on the animation that you were seeing at the bottom, we are basically walking along this low-dimensional space, which is usually 10-dimensional, and the output you are seeing in the screen is basically a decoded version of those points in that space. Now, what should be the pose representation? What are the design choices that we should adhere to? So there are a lot of questions. I'm not going to go into much detail here, but there are questions like whether you should do allocentric or egocentric representations. So allocentric means we want to represent a pose of the camera with respect to object, or egocentric is where you want to represent the pose of the object with respect to the camera. It turns out that if you are making your prediction on top of ROI features, it's better to do allocentric, and that's what we use. Similarly, for representing the location of the object, it's not a good idea to directly train for the XYZ location of the object. So instead, what we do, we train to predict the 2D projection of the object center and also an A-model bounding box. And with all these three information, it's good enough to get the actual 3D location of an object. So our pose representation is basically divided into these three parts, like a model bounding box, center projection, and pose angles. The a model bounding box and center projection are actually 2D targets. Right? So now, before I move on, I want to briefly talk about equivariance. So this is a slide from Kai-Ming He, where he shows that for the task of detection and mask, it's very important to maintain equivariance. So if you have a bigger apple, you want your detection box or mask to also be bigger, right? But if you think about ROI pooling, it doesn't preserve equivariance. It makes an invariant representation because the alloy is resized to some fixed size, like 7 by 7 or 14 by 14. Now, for tasks like detection boxes and mask, this is very easy to do because you can do a normalization, and when you want to get the output, you can unnormalize it. But this normalization and unnormalization is easy to do only for 2D targets. So for the targets like the A-model bounding box and the center projection, we can do this denormalization. But this denormalization doesn't make any sense for 3D targets like shape and pose. So how do we capture that? So to illustrate the problem, I'm showing this picture where on the top you have this 3%. All of them have exact same shape parameters, right? So on the bottom, if you have been doing if you do the ROI pooling on the RGB image directly, that's how they will look like. Now, if you are not normalizing them, you are asking the network to predict the same shape parameters because all these 3% are the same guy, right? So they have the same shape parameters. And because you are not normalizing them, it's very hard for the neural network to predict it correctly. So how do we solve this problem? So one way to think of the ROI pooling process as an image captured by a virtual camera, which is kind of zoomed in, which basically it has a different intrinsics, and is slightly rotated and looking at a different part of the image, right? So we can compute the intrinsics of this virtual camera, and then two cameras, which are just related by a pure rotation, are related by this infinite homography matrix. So this 3x3 matrix, which gives us these 9 parameters, basically captures all the transformation that's being done by the ROI pooling process. So all we do is basically feed these 9 parameters to the shape and pose classifier. So now they have a better chance of getting a more equivariant output. So now let's talk about training. So let's assume you have direct ground truth for 3D shape and pose. So then you can just easily apply direct ground loss to these targets and train them. So one specific thing is that for shape and pose, we do a combination of regression and classification loss. But the problem is, for real-world data, it's very hard to get ground truth 3D shape. Right? So how do you solve this problem? So our insight is that even though 3D ground truth is hard to obtain, but it is very easy to obtain or annotate 2D ground truth. Like, for example, it's very common to have instant segmentation, like in Kitty and Pascal and a lot of different data sets, right? So the thing is, we are predicting the shape and pose parameters, right? So from there, we get the full 3D shape, and we can actually render it and render an instant segmentation. And we can compare this instant segmentation, rendered instant segmentation with the ground truth instant segmentation. And we can backpropagate that loss all the way back. Now, the problem is this rendering is being done through OpenGL, which is almost like a black box. So how do we get derivatives out of it? So our solution was to use finite derivatives. And the reason we can use this is because we have very less number of parameters. For example, for a rigid object, we have only 19 parameters. So we need to run this renderer 19 times, right? So now at inference, we do not have to do this render and compare stage, and it's just a simple fast-forward pass. And so the overhead on top of faster RCNN is very minimal. So under 200 milliseconds, you get the shape and pose of all object instances. So let's look at some of the results. So this is some results on joint detection and pose estimation on the Pascal 3D dataset. So here we use this metric called average viewpoint precision, which is very similar to the average precision metric for object detection. but just that additionally, the pose needs to be below some threshold. And as you can see, our numbers are normally always more than 10 points from the previous state of the art. So here I'm showing some qualitative results on QT dataset. So on the left is the input image. Then on the middle is our 3D object reconstructions, right? That's our output. And now we also kind of render those 3D reconstructions from the point of view of the camera and overlay them on the image. So you get instant segmentation for free, right? And so we also do quantitative experiments on KT, and we found out that it's pretty good pose accuracy. So these are some results on Surreal dataset. So in Surreal, they actually train one network for estimating body depth, and then another network for predicting body parts. Now, our method directly predicts the 3D shape and pose, and we just render the depth and the segmentation. So with just one network, we can predict both of them. So you do not need to have two separate networks for depth and another for segmentation. Now, before I conclude, I want to take a step back and kind of compare with some of the modern inverse graphics architecture. So on the bottom, what you are seeing is this work from Kulkarni et al. Called Deep Convolutional Inverse Graphics Network. So they use an autoencoder idea where the bottleneck part is basically learning the graphics code. So the first part, the encoder part, is similar. So it's learning to do de-rendering. For them, they use a decoder to learn how to render. For us, the rendering part is explicit, so there's no additional learnable parameters. Plus, additionally, to gain interpretability, the deep IGN work, they have to train the network with specific forms of data. But here, interpretability is there by design. So those are some of the nice things I think should be concerned when we design the next inverse graphics architecture. So these are the summary of the work. So we present a fast inverse graphics network. We present deep differential render and compare, which allows us to exploit 2D annotations. With that, I will conclude my talk. Thanks a lot for paying attention.
We have time for a couple questions. Yes.
Okay. Thank you for this very nice talk. Okay. So I'm just wondering, you separate this pose and the shape, okay, into different network paths. Since essentially you are just regressing all those parameters. So can you combine them together, just have one path?
So I guess your question is pose and shape are through two passes?
Yeah, you separate them into two passes. So is it okay to just combine them?
So they are not two passes, they are just two heads, right? For example, if you might be familiar with mask CNN, so there is one head which is doing mask prediction, then maybe there's another head which is doing key point. So they are working simultaneously. They are not separate passes.
I see. Thank you.
Yeah, another question over here? Or? Oh, okay. Let's go to this side.
Can you hear me? Okay,
Yeah.
great.
Yeah.
Okay, thanks, Abhijit, for the talk. I wanted to ask about the number of parameters and the relation to finite differences. So you're able to take finite differences at this point because the number of parameters are smaller.
Yes.
And how does that scale as the number of parameters in the rendering pipeline increase, meaning for more complex 3D rendering, basically?
Yeah. So that's a very good question. So with finite differences, specifically the central differences scheme, so the order of complexity is order of n, where n being the number of parameters. So the reason we are using that, because our parameterization is very compact, which is, you can also say, is something desirable. You want your scene representation to be compact. Now, there are also approximations which are like order of 1. like SPSA. But yeah, we haven't explored that yet.
Okay, thanks.
And one last question.
I understand that the shape basis is a crucial component of your work that greatly reduces the variance of shapes. But in the future, do you have any plans to incorporate novel or even non-conventional shape that is beyond what you have in the shape templates?
Yeah. So I guess, in this work, we are showing a very simple shape space just by using PCA. And if you think about the shape space that we use for persons, it's totally different, like simple model. Still PCA. So I think at the point our framework is not explicit shape representation. You can have your own shape representation as long it is fast to decode and continuous and low dimensional.
Okay, thank you.
Hey, let's thank Abhijit again. And while we're switching speakers, any spotlight presenters for later in this session, please come sit in the front 2 rows here.
Apologize for the delay. So for the next speaker, we have a talk from Wenjie. It's called Fast and Furious Real-Time End-to-End 3D Detection, Tracking, and Motion Forecasting with a Single Convolutional Net.
Okay, thanks, Surawasu. Good morning, everyone. My name is Wenjie. Today, I'm presenting our work titled Fast and Furious Real-Time End-to-End 3D Detection, Tracking, and Motion Forecasting with a Single Convolutional Net. This is a joint work with Singh and Raquel from Uber ATG and the University of Toronto. So self-driving is super exciting. It is going to transform the way we live. Long time ago, we used to train horses to take us home. Nowadays, we're training robots to move everybody, everything, everywhere. However, self-driving is in fact a complex and hard problem. To solve this task, we often explore 3D sensor data, such as LiDAR. Here I'm showing a top-down view of LiDAR point cloud. Given this sensor input, we first need to localize ourselves and retrieve map of the environment. Next, we need to detect the surrounding objects, such as vehicles, pedestrians, and cyclists. That's not enough. We also need to track them across time as well. This is shown here by a different color for each object. Furthermore, we have to predict where each object goes in the future. And this is represented by waypoints in this image. Now, motion planning will take all this input and output EagleCast trajectory. And finally, a controller will output the vehicle command to execute this trajectory. As we can see, self-driving is indeed a complex problem. Many approaches have been...
Yeah. Can you check your connection? It's flickering a lot.
Okay. try this. Okay, I think I'll continue. All right, so in this work, we are tackling detection, tracking, and prediction, with the focus on vehicles. So before, many approaches have been proposed to solve each of these individual tasks. For example, FAST and MASTA-CN, YOLO SSD focus on 2D object detection. Recently, 3D object detection has become popular. Also, Fichten-Hoover proposed to do 2D detection and tracking in the image domain. Methods such as social LSTM and desire perform behavior and trajectory prediction. However, in the context of self-driving, this modular approach is suboptimal as uncertainty is not propagated during training between different modules. And it is computationally expensive as heavy feature computation not being shared. In contrast, we propose to do joint modeling using one network for 3 tasks. Our approach goes directly from sensors to track the bounding boxes and the future location for all objects at once. Our motivation is that learning jointly can fix the distribution mismatch between different modules and provide a better global solution. Also, sharing feature computation between different modules and objects will result in much efficient solutions. Our approach, named FAF, is a single thing for 3D detection, motion forecasting, and tracking. Importantly, it learns to leverage temporal information and runs real-time at 30 milliseconds per frame. Here is an overview of our approach. We utilize 5 past LiDAR sweeps as input. This allows us to estimate motion robustly. In the middle is a CNN that learns from temporal information and predicts bounding boxes for multiple time steps. Lastly, we aggregate detection and prediction to output the tracked bounding boxes with corresponding future waypoints. Now I will introduce details for each part. First of all, we follow a single-stage detector approach, where the CNN is used to extract features from sensor and output detection directly without ROI pooling. We use a voxel representation as input, where each voxel is a binary indicator of whether it contains LiDAR points. We treat high dimension as feature dimension, as it allows the network to learn better representations more efficiently. Note that with the extra time dimension, our input is a 4D tensor. As regression targets, we use multiple anchors for each feature location and regress directly to the position offset with respect to each anchor, as well as their corresponding box size and heading. This figure at the bottom shows an example with a positive anchor in red and ground truth bounding boxes in blue. For the backbone network, we explore 2 ways to fuse time information, considering the trade-off between running time and accuracy. The early fusion model shown on the left uses a 1D convolution to aggregate time information at the very first layer and perform 2D convolution afterwards. It is very fast, as aggregation is done at the very beginning of the network. On the right-hand side, the later fusion model uses 3D convolution layers in between to learn more complex motion features, but it is less efficient than the early fusion model. Given the CNN features, we use fully connected layer on top to predict the vehicle's current and future location. So in this animation, the left solid blue car represents the current detection, and the 2 light blue cars on the right represent future predictions. Now moving to the next step, we detect another red car. As our current detection overlaps with previous forecasting, we can confidently say that they're actually the same car. So we can propagate the track ID and get our tracklets. So in order to benchmark our work, we collected a large-scale data set called Uber 204D. So it contains the sequences with accurate equal poles that allows us to do multiple tasks jointly. As comparing to existing data sets such as Kitty, Uber 204D has 6,500 scenarios with 1.6 million frames, while each frame contains more objects seen from 360 degrees and up to 120 meters away. As we can see in this figure of the label distribution, 204D provides richer surrounding information than Kitty. Also, it was collected over a long period of time in several seasons and different weather conditions during day and night and across multiple cities. Thus, this is more representative for real-world driving cases. So now let's look at some qualitative results first. This video shows a top-down view with detected oriented bounding boxes. So tracking information is represented by color, and we can see it's very consistent over time. In addition, we use waypoints to represent each vehicle's future motion. This video shows different scenarios, including heavy traffic as well as rare cases. For example, we can see this blue car in the middle is trying to back up. Also, by looking at the waypoints, we can tell whether cars are moving very fast. For example, those yellow cars in the middle, or cars, they are static, where all the waypoints will be overlapped. For example, we can see some static car in the middle here. And the next, we will have a sequence of a turning case and more sequence on the heavy traffic road. Next, let's look at some quantitative results. As shown in this table, our approach results in significant AP improvement for all IOU thresholds. For example, at IOU 0.7, FAF is 5 points better than MobileNet and it runs faster, requiring only 30 milliseconds. Here we show MAP as a function of object's distance to the ego car. We can see FAF is better at all range, especially at the long range where it's more difficult to perform detection. Also, we know that LiDAR points are sparse. Some vehicles would only have a few LiDAR points on them. Thus here we show MAP as a function of the minimal number of points for all vehicles. As we can see, FAF outperforms at all thresholds. In these slides, we show tracking and motion forecasting performance. Our prediction error is less than 0.4 meters at 1 second into future, while on the right-hand side, we can see that if FAF outperforms standard Hungarian tracking, which uses the same detection output. And this slide shows an ablation study. The takeaway here is that using multiple LiDAR sweeps as input can improve detection. And it's important to explore time information. More importantly, if we join reasoning with prediction and tracking, we achieve the best performance, which is 6 points better than using a single sweep data on the 0.7 IOU threshold. To summarize, we propose a single neural network that performs joint detection and motion forecasting with a simple but effective way to decode the tracklets. We improve both on accuracy and the runtime, which is crucial for self-driving. As future directions, we plan to explore HD map as well as multi-sensor data like images and radar. So with that, I conclude my talk, and I welcome everybody to the poster at A4. Thank you.
We have time for 1 or 2 questions.
Beautiful work, thank you. Are you planning to release the data set, and if so, when?
Yes.
As to the second part of the question?
I think we are working on finalizing the data set and some logistic issue to fix. But I think we're going to release it probably soon. Yeah.
Wonderful, thank you.
Yeah.
Let's take a question on the other side.
All right. So my question is, it seems that the scenario at the intersection is more interested than the road between intersections. Did you do sample balancing or not? And if you do, how did you do it?
So our data set already considered the variety of the scenario. So that's why we have a lot more objects in each frame. So yeah, that's what we already have. Yeah.
Let's do one more question, the last one from this side.
Okay.
You mentioned that one of the advantages of your approach compared to a more modular solution was that it could propagate uncertainties across different components. I was wondering, in your stack, do you do any explicit modeling of the uncertainties through like position covariances or multiple predicted trajectories, or is that still sort of a future?
I think I didn't get the second part.
Do you explicitly model uncertainties in your output with like position covariances or like multiple trajectory possibilities, or is that not currently part of your solution?
Yeah, in this current version, no. So in current version, we hope the network to learn that. That's it. But we are actively looking into that. Yeah.
Thank you.
Let's thank the speaker again.
Our next talk is on scale invariance in object detection. The authors are Bharat Singh and Larry Davis, and Bharat will be giving the talk.
Hello everyone, I am Bharat and I am going to present our work and analysis of scale invariance in object detection. This is joint work with Larry Davis at University of Maryland. So let us start with this question, like what makes object detection different from image classification? Now to answer this question, let us look at the median scale of objects relative to the image in ImageNet and COCO. So as we can see, the median scale of objects in ImageNet is 0.5, while that in COCO is 0.1. So that means that there are many small objects in detection datasets. Now let us look at the smallest and largest 10% objects in COCO. So as we can see, there is a scale variation of like 20 times. So not only are there many small objects, but there is also a large variation in the scale of the objects. Now, modern object detection pipelines are based on convolutional neural networks, and these networks are typically pre-trained for tasks like image classification. Now, although the resolution of the input image is much higher, like the features of the resolution of the layers which contain high-level semantic information is much lower. So this makes it difficult to use convolutional neural networks for tasks like object detection. So to solve this problem, multiple architectural changes have been proposed. For example, in scale-dependent pooling, if we have smaller ROIs, we'll pool features from higher resolution layers. If we have larger ROIs, we pool features from coarser layers. Feature pyramid networks combine features from multiple layers of the network, and they also make predictions at multiple feature resolutions. Okay, now to increase the resolution of the conf5 feature map, it is also common to employ dilated convolutions. And deformable convolutions further improve upon this idea, and they adaptively change this dilation factor. Okay, but the features of shallower layers like conf3 and conf4, although their resolution is much higher, they do not contain the rich semantic representation which is present in deeper layers like conf5. And moreover, if we compute the same conf5 feature map at multiple image scales, the semantic representation which they will have would be different. So although we can make architectural changes, we feel that image pyramids have something more to offer. Okay, so let us look at some current practices in object detection. So typical data sets like Pascal or Coco, they have a resolution of like 400 by 600 pixels. Now, during training, these images are upsampled to a resolution of 800 by 1200 pixels. I mean, this is most generally the case. Okay, but during inference, what happens is these images are further upsampled, and this brings in some improvement for small objects. Now, it is important to note that these resolutions are typically not included during training. Now, because this practice of upsampling during inference is so common, we would like to design some experiments so that we understand whether CNNs are actually robust to these upsampling artifacts. So this is what we do. We take high resolution images in ImageNet, and then we create their downsampled versions. And then we upsample these images to a resolution of 224 by 224 so that we can classify them using like standard connets like ResNet 101. Now, because these networks are trained at a resolution of 224, we call this network CNNB. Okay, so let us see how CNNB performs. Now, as we can see, for 48 by 48 pixel images, we see a drop in performance of like 43%. So does it look like CNNs are robust to these upsampling artifacts? Well, doesn't seem to be the case. Okay, so since training and testing on different resolutions is not optimal, what all alternatives do we have? So we can train specialized architectures for detecting objects of different resolutions, or we can resample the input data so that the same network can be used to classify objects of different sizes. Okay, so let us first try to change the architecture. So ImageNet architectures typically have a stride of 2 and a pooling layer early on in the network. So if we have small objects, we have to upsample the image so that we can use this network to classify small objects. Okay, now if we have a CFAR10 style architecture, they do not have this pooling layer or a stride of 2 in the beginning of the network. So we can just use small images, and we don't need to upsample them, and we can classify them using a CFAR10 style network. Now, because this network is trained on small images, we call it CNNS. So let us see like how CNNS performs. So as you can see here, for small objects, we see a performance improvement of like 26.5%. So it's pretty clear that resolution-specific classifiers are much better. Now let us explore the other option of resampling images. So this is what we do. So we have this high resolution, our previous network which was trained on high resolution images, which is CNNB. And then we fine tune it on upsampled low resolution images. And we call this network CNNBFT. Okay, so as we can see in this slide that CNNBFT performs much better than CNNS. So what does this tell us? It tells us that pre-training on high resolution images actually helps us to classify these low resolution objects. Okay, now as we have learned that ImageNet type CNNs which are fine-tuned on like upsampled images are much better than CFAR10 style architectures, we would like to explore the design space in this particular direction for training object detectors. Now an interesting question to ask is like, should we train on all object sizes to maximize the variation in data? Or should we try to maximize the variation, minimize the variation in scale by training on rescaled objects within a desired resolution range? Okay, so because we need to actually train detectors to answer these questions, I would first describe the experimental setup. So in this case, we extract 300 proposals using RPN at a resolution of like 800 by 1200 pixels. And to classify these proposals, we use a deformable RFCN detector. And to avoid memory issues, we use a ResNet 50 backbone. And during inference, we upsample the images to a resolution of like 1400 by 2000 pixels. And performance is only evaluated for small objects in the COCO 2017 test dev set for the bounding box detection task. Okay, so let us look at the common case of like training on 800 by 1200 pixel images. And in this case, we use all the ROIs to train our network. Now, this network obtains an MAP of like 19.6%. Now, we can use exactly the same procedure, but trained on 1400 by 2000 pixel images. Now, in this case, there is no difference in resolution between training and inference. But surprisingly, even this method only obtains an improvement of like 0.3%. So it's possible that although it is easier for us to classify these small objects, due to the limited receptive field of the CNN, it is much harder to classify the larger objects. So what we do is we got rid of the larger objects and trained a network only on small objects. Now, what we saw was much surprising, that in this case, the performance dropped even further. So what happened here was, although we minimized the variation in scale, we also lost a lot of training samples. And in this case, we lost like 30% of the training samples. So what this means is, it is very important to utilize all the training samples which are available in your training set. Okay, so then what we do is we create an image pyramid, and we generate images in which we generate images at multiple scales. And we use all the proposals to train in each of these scales. Now, what we found is that even this network only got like 19.5%. So again, my hypothesis is that like in low resolution images like 480 by 640, we have small objects and they are hard to classify. And as we saw before, like in 1400 by 2000 pixel images, it is hard to classify the very large objects. Okay, so whatever upsampling methods we discussed so far, like they do not even outperform the like 800 by 1200 pixel baseline comprehensively. So none of these, so what should we do? Like, it seems that we need a method which can reduce the variation in scale without reducing the total number of training samples. So for this, we propose scale normalization for image pyramids, so, which is also called as SNIP. And SNIP is just like multi-scale training. What it does is that it does not backpropagate gradients for ROIs which do not fall in a desired scale range. Now, SNIP obtains a significant improvement in performance over all the previous baselines we had just discussed. So let us revisit the whole pipeline again. We construct an image pyramid and extract region proposals at each scale. And then for each scale, we have a desired scale range which determines if a proposal is valid or not. We only include valid proposals during training. And during inference, we rescale these detections after bounding box regression to image coordinates. And finally, we use soft NMS to combine these detections. So here is the takeaway. Training on all samples increases the variation in appearance and pose, which helps us to perform better classification. But classification networks are trained at a fixed resolution. And a scale-specific design reduces the domain shift for the classification network during fine-tuning. And this is precisely what SNIP does. It effectively utilizes all the training samples while reducing the domain shift for the pre-trained network. So let us look at some of the results. So for training RPN, we obtain a 6.3% improvement in recall for 0 to 25 pixel objects. And at 50% recall, we get like 2.9% improvement for average recall. We also present results for object detection on the COCO 2017 test dev set. And we get a 3.5% improvement for the deformable RFCN detector. And for faster RCNN, we get like 1.9%. Okay, so are there any drawbacks of SNIP? Well, it is 2.5 times slower per epoch, so that's really bad. So if you don't like to wait, you should check out Sniper, and code for Sniper is available on GitHub, on Mahir's GitHub page. And this makes training much faster. I hope that you would prefer this one compared to SNIP because it does exactly what SNIP does, but it's much better. And I'm happy to take questions.
We have time for a couple questions. There are microphones to either side. Yes.
Thank you for your work. So you pre-trained models on ImageNet at different resolutions. Which model did you use for the detector?
So on ImageNet, we use ResNet 101 for classification. And for detection, we tried like multiple backbones like ResNet 101, DPN, and
which resolution was it pre-trained on?
The detectors or the classifiers?
The classifiers.
In ImageNet?
Yes.
So ImageNet, the detectors which we use were trained on 224 by 224.
And have you tried different ones?
Pardon me?
Have you tried different resolutions?
On image. Oh yeah, so on ImageNet we only we only start with 224 by 224. So already these networks have some they're trained with multiple scales of the object. It's inbuilt in the deep learning libraries.
Thank you.
Do we have one more quick question?
Yes. Thanks for your nice talk. And I have a question here is, have you ever compared or maybe have you ever done any of the human tests to see by using the larger high resolution imaging to help for the object detections? Basically, it's trying to see our human also have this similar mechanism or not. Did you get my question?
Yes.
So from your talk, it looks like by using a high resolution image for training, going to help for the testing even for low resolution, right?
Yeah. So basically.
And my question is this thing is also happens in our human like the as
yeah.
a human?
So I agree. If you think of it from a human perspective, if we have seen something in a better quality, maybe if you've seen high resolution cats before or some high resolution objects before, and in another case you haven't seen these high resolution objects. When you see low resolution objects, I think it will be easier for you to even recognize them. So I think that this might be happening also in CNNs.
Okay. So have you ever done any of the quantitatively
Yeah,
experiments to compare?
Yeah, so we haven't done these experiments on human subjects, trying to show them if it is easier for them. But I believe so that it would be an interesting experiment to try out maybe in neuroscience or.
Okay,
but even it could be done by vision researchers. Yeah.
Okay. Thank you.
Okay, let's thank Bharat again.
So the last talk in this session, we have relation networks for object detection, which will be presented by Han Yu.
Thanks for the introduction. Good morning, everyone. This is Han from Microsoft Research Asia. The title of this presentation is Relation Networks for Object Detection. It's a joint work with Jiayuan, Zheng, Jifeng, and Yichen. In the past few years, convolutional neural networks have been used almost everywhere in computer vision, for both high-level and low-level visual tasks. Basically, convolutional neural networks try to model relation between elements of different levels. For example, the convolution layer models relation between neighboring pixels. For another example, the RY pooling plus fully collected layer models relation between nearby region paths. These two layers are so widely used in various visual tasks. It's hard to imagine a vision world without these two layers. Why are they so popular and even indispensable? From my understanding, one important reason is that they are effective and very easy to use. They are parallel, indicating high efficiency. They are learnable and require no relation separation. They are translational invariant, which is an important property for many visual tasks. And the convolution layer is also stackable. A lateral question is, what about object-object relation? Actually, object-object relation is a well-recognized problem which could help visual perception. For example, in this image, it's much easier to detect the baseball glove if we know there is a person below. However, modeling of object-object relation is rarely studied in the deep learning era. Perhaps one reason is the irregularities of objects. The objects can be at arbitrary locations of different scales within different categories and even a very number across different images. This is very different from labeling pixels and region paths, which are organized in grid. So the way of convolution and RI pooling layers in modeling of pixel-pixel and part-part relation cannot be directly applied here. In this work, we would like to design a simple module to model relation between objects. We call this module as object relation module. We hope this module is effective and very easy to use. So it can serve as a basic component to support various applications of object level and scene level understanding. Concretely, we hope it has the same good properties as convolution and RI pooling layers, that it's parallel, learnable, require low relation separation, translational invariant, and stackable. So what is object relation module? Basically, it's an extension of the attention module, which has been widely used in the field of natural language processing to model sequential data. For example, the relation between word and word. In this work, we extend this module to model relation between objects, between 2D irregular objects. Specifically, in standard attention module, many appearance feature is used to measure relation between elements. The appearance feature is firstly projected into a subspace, and then in a subspace, we measure how well two elements match each other by dot product. For relation between objects, the spatial arrangement plays an important role. So we propose another geometric weight to model the spatial relationship between two objects. We use the four-dimensional bounding box regression vector as input, then go through a small network and produce the geometric weight. Because the four-dimensional bounding box regression vector is translational and scale invariant, the produced geometric weight is also translational and scale invariant. The proposed geometric weight proves important in our experiments. We will show it later. Using this joint weight of appearance and geometry, which indicates how well two objects are related, we aggregate information from all objects by weighted sum of the input appearance feature to produce the relation feature of one object. So this is one branch of relation computation. Actually, we don't use a single branch, we use multiple branches. The intuition is that the relation between objects can be of multiple types. So we may need a different branch to encode different type of relation. Finally, we combine the multi-branch relation feature with the original input appearance feature to produce the final output. We use residual structure here because residual collection is an efficient way to merge two signals. And it can also facilitate our optimization. To summarize, the proposed object relation module has the same dimension of input and output. It's effective and very easy to use, so we believe it can support various applications of object level and scene level understanding. Next, we show its application in the problem of object detection. The state-of-the-art object detection methods mostly follow the region-based paradigm. Here shows one such example, fast or FAST-RCN, which is perhaps the most widely used method for object detection. We mainly focus on the part of network which processes regions. Given region proposals, we first do instance regulation. In this step, each region proposal is separately classified by a small network. such as two fully collected layers. We believe this step is suboptimal than joint inference. Then we do duplicate removal. Why do we need this step? It's because in previous step, any proposal with sufficient overlap with the ground truth are labeled positive. So for each ground truth object, we may get multiple detections. To produce exactly one detection for one ground truth, we need to do duplicate removal. For this step, long maximum suppression is perhaps the most widely used method, which is handcrafted. We also believe this step is suboptimal because nowadays we almost always prefer learnable methods than handcrafted ones. Here is our method. Our method is very simple. It's a simple modification of the fast rsync pipeline. Basically, because object recognition module is in place, so we can insert it into the instance regulation and duplicate removal steps of object detection. For instance regulation, the modules are inserted after two fully collected layers respectively. For duplicate removal, the application is a bit more complex. In this step, the object recognition module is used to produce a long duplicate score to evaluate whether the object is a duplicate or not. We multiply this score with the original score and to produce the final detection score. Finally, by learning all steps jointly, we achieve the first fully end-to-end object detector. Next, I'm going to show our results. We firstly study the application in the instance regulation step of object detection. By using default settings, we achieve 2.3 improvements using two object recognition modules with about 3% more computation. By using more modules, for example, 8 ones, another about 1 point improvement is achieved. We also study the individual designs of our object recognition module. This comparison shows the importance of the proposed geometric weight. Without this term, the accuracy drops by 1.6. This comparison shows the importance of multi-branch relation. Without multi-branch, the accuracy drops by 1.4. This comparison shows the importance of residue collection. Without residue collection, the accuracy drops by 1 point. Next, we show results for duplicate removal. For all these experiments, we assume a standard fast RC model has been trained. All these methods use the same output of this fast RC model as input. We can see from this table that our method is noticeably better than MS method and slightly better than soft MS method. We then train all steps in an end-to-end fashion, and additional 0.5 improvement is observed. On stronger backbones such as feature pyramidal network and deformal convolutions, we also have moderate improvements with small computation overhead. Next, I'm going to show some study on what kind of relations are learned. Firstly, we show some examples with high relation weights. The left figure shows the learned relation in the instance recognition step. It can be seen that semantic-related object pairs are learned. The right figure shows the learned relation in the duplicate removal step. It can be seen overlapped objects of the same ground truth are learned. These results demonstrate that object recognition module can be driven by individual tasks. And in different tasks, we may learn different types of relation. Here we show another interesting observation. The left figure shows classical occurrence matrix and COCO counted using ground truth annotation. The right figure shows learned average attention weights between objects of different classes in instance regulation step. We can see that they are highly correlated. Actually, the correlation coefficient is 0.9, which is very high. This indicates that the classical coherence information is implicitly learned. In conclusion, in this work, we first propose another object relation module to model relation between objects, which is effective and very easy to use. So we believe it can support various applications of object level and scene level understanding. Then we demonstrate its application in a problem of object detection. It improves detection accuracy. In addition, we developed the first fully end-to-end object detector. It's worth noting that the module is general, so the application should be beyond object detection. If you are interested, please come to our poster at A10. You can also try our code on GitHub. That's all. Thank you.
There's time for a couple of questions.
Thank you for such an interesting talk. I'm wondering if you've thought about applying this module to single-shot detector approaches like SSD or YOLO, which have a very dense grid of predictions, and if that would be computationally efficient.
You mean applying our module to very dense region proposal or dense anchors?
Yes, exactly.
Okay. Actually, it's a very good question. To be honest, it's now not efficient to apply our modules to dense anchors or dense region proposals. It's because we use dense pairwise relation. As you know, our module is the complexity of our module is proportional to the square of region proposal numbers. So it will be very time consuming to apply it in the dense region proposals. However, actually, dense relation pair is redundant. So I think if you take some sampling strategy, then you can make it efficient for dense proposals. Yeah.
Thank you.
Any other questions? Okay, so if you have no more questions, this concludes the oral session for this section. So let's thank all the speakers again. So we now have the spotlight sessions. There'll be 10 fantastic spotlight talks. We ask the speakers to line up one side of the stage in order of your presentations, and each of you will have 4 minutes, okay?
Hi, everyone. My name is Fan Zhu. I'm representing the original authors of the paper to introduce the work, Zero Short Sketch Image Hashing. This task is all about learning binary features to present the semantic content of data for similarity search in Hamming space. This is widely considered to be more efficient than computing real-valued feature similarity. However, existing research in this field suffers from several problems. One is that existing hashing models are not able to handle the problem of train test category exclusion. Those categories of data that have never been seen during training are not well recognized by hashing models, and the resulted codes are impacted for similarity search. As a result, A new problem of zero-shot retrieval is then defined to encode data from unseen category. In this work, we extend this problem to a cross-model hashing scheme and investigate the algorithm performance with the task of sketch-based image retrieval. And with that, we follow mainstream themes to design our hashing neural network. First of all, not all regions in an image or sketch are informative for cross-model mapping, and we introduce the attention mechanism for this purpose. Secondly, the heterogeneity between image and sketch data needs to be migrated during training. So we employ a 3 network structure and a connector layer. Finally, for zero-shot tasks, it is important to transfer semantic knowledge from seen to unseen classes. Here, stochastic semantic decoder and graph convolution layers are involved for this purpose. And with that, we have the network structure shown here, which basically includes 3 parts. 2 for encoding the corresponding modality of data, and 1 as a code render. During training, image sketch pairs are rendered to the network. The connector layer fuses the hidden representations of the image and the sketch pairs. Category level semantic similarity is used in the graph convolution layers to relate the data points using semantic knowledge for our zero-shot task. This is further enhanced by the decoder. The render code space can be generalized to unseen categories as the semantic knowledge defines the relation between concepts. Here, we also briefly describe the graph convolution. Considering each sketchy image pair in the training batch as a vertex of a graph, the graph convolution operation with the trainable filter G can be approximated by a linear transformation with an additional affinity matrix A, which can be determined by the category semantic representation. In this work, we specifically use a word vector for this purpose. The learning objective is inspired by the variational autoencoder with the Martinelli prior, allowing stochastic gradient descent for training. We conduct experiments on 2 datasets, Sketchy and TU Berlin, both with a zero-shot setting. We'll compare our model with the state-of-the-art cross-model hashing, zero-shot learning, and sketch-based image retrieval algorithms. Results show that the existing works generally fail in this task, while our model works very well. We also compare this model with our previous work on the sketch-based image retrieval hashing. It can be seen that this model produces more accurate retrieval candidates. Since the authors cannot be here today, so if you have any questions, please drop them an email. Thanks for your attention.
My name is Danna Gurari, and I'm going to share about our team's work on answering visual questions from blind people. Questions such as, is this shirt dirty or clean? And what flavor is this? May seem trivial to many of you. But for people who are blind, such questions are obstacles that can significantly impede them in their daily tasks. Nearly 10 years ago, a mobile phone application called VizWiz was released to help blind people answer such visual questions. With this application, a user could double-click on the phone to take a picture, then double-click on the phone to record a question about the image, and then have both sent to a team of crowd workers, who in turn would provide an answer. Over 11,000 people used this application to ask over 70,000 visual questions between 2011 and 2015. The goal for our work is to teach computers to automatically answer visual questions asked by blind people. For this purpose, we use visual questions collected with VizWiz application to build the first data set that originates from blind people. Our VizWiz data set is the first visual question answering data set arising from a natural setting where real users were asking questions about images to support their real daily needs. Towards preserving anonymity, we transcribed each audio recorded question to remove voice and resaved each image to remove metadata, such as the location where the picture was taken. We next removed all visual questions that contained personal information, such as financial statements, prescription pills, faces, addresses on personal mail, computer login credentials, and nudity. Finally, we crowdsourced 10 answers per visual question to support algorithm evaluation. In total, the final data set includes over 30,000 visual questions and over 300,000 answers. We next examined the diversity of questions, images, and answers in the data set. We show visually the frequency that questions begin with different words using a sunburst diagram. The most common question is the basic recognition question of, what is this? Questions also regularly begin with a rare first word, such as please, hi, or okay. This illustrates that spoken questions can be more conversational. For images, we found that roughly 1 in 4 were deemed to have an unsuitable image for answering the visual question. Such low-quality images arose due to poor lighting, poor focus, and poor framing. For answers, roughly 1 out of every 4 visual questions could not be answered by crowd workers. We show here the popularity of answers for answerable visual questions, with the text size proportional to the answer frequency. Popular answers include yes, no, white, gray, and blue. Rare answers include incomprehensible combinations of letters that can solve a CAPTCHA. We concluded this work by assessing the difficulty of the dataset for modern algorithms. We benchmarked 9 methods for the task of predicting the answer to a visual question. We also benchmarked 8 methods for the task of predicting if a visual question can be answered. Results show the VizWiz dataset is difficult for modern vision algorithms, and that is the motivation behind our challenge for the community. We invite each of you to partake in our challenge at ECCV to design algorithms that may one day help blind people overcome their daily visual challenges. Thank you.
Hi all, I'm Deepak from Indian Institute of Science. Our work tackles the problem of crowd counting using an incrementally growing CNN. Automated counting of people in dense crowds images is a challenging task. The major difficulty stems from the large diversity in the way people appear. There are severe pose, scale, and density variations along with background clutter in typical crowd scenes. Current approaches use CNN to regress a crowd density map, which on integrating gives a count. However, single CNN regressors may not be sufficient to capture the huge diversity. Our solution is to have multiple regressors where each net is specialized on a particular crowd type like dense, sparse, etc. This architecture has a set of expert regressors and a classifier. For a test image, patches are extracted and routed to the appropriate expert regressors by the classifier. However, the important question here is how to create experts without any manually specified criteria for forming specialties. Naive mixture of expert methods is unable to adapt with the huge diversity and performs poorly in this scenario. We handle this problem with the growing CNN, which can progressively increase its capacity based on the complexity of the dataset. Our model IGCNN starts from a base CNN regressor, which is trained on the full dataset containing all types of crowds. In order to adapt with the diversity, we create 2 child regressors which are exact copies of the base CNN. A differential training procedure jointly divides the dataset into 2 clusters and fine-tunes the child networks on their respective specialties. The basic idea is to backpropagate only the regressor with minimum count error for every input patch. Consequently, without any handcrafted criteria for forming specialties, the child regressors become experts on certain types of crowds. The child networks are again split recursively, creating 2 experts at every division. This hierarchical differential training leads to a CNN tree where the child regressors are more fine experts than any of their parents. Note that the objective of this training is to create a set of fine experts, and the hierarchy is discarded after training. The number of experts created depends on the complexity of the dataset and is inferred automatically. The leaf nodes are taken as a final expert, and a classifier network is then trained. For a given test image patch, the classifier is optimized to predict the label corresponding to the best expert regressor. The hierarchical tree splitting is stopped when the actual count accuracy with the classifier on validation set is not improving. The major metric of evaluation is the mean absolute error of count predictions over the test set. The proposed model achieves higher count accuracy on major crowd datasets. For example, on Shanghai Tech datasets, we grow IGCNN to 3 level with 8 expert regressors and achieves better accuracy. We also evaluate the effect of hierarchical training on performance. Starting from the base CNN, along the hierarchy, we see the count errors dropping. But after a certain level, the performance saturates. This is due to the poor generalization down the hierarchy because of less training data. Further, we analyze the characteristics of specialties mined automatically by our method. For this, we compute the distribution of crowd counts on the specialty subsets of the expert regressors. Interestingly, we observe a possible clustering of crowd patches based on density. This shows that our method automatically creates experts based on certain latent factors correlated with crowd density. We believe that the creation of experts in this manner is an elegant and essential paradigm to handle tasks with huge variation in input. For more details, please visit our poster. Thank you all.
Hi, I'm Jong-Hin Choi from Allen Institute for Artificial Intelligence, or AI2 for short. I'll talk about structured SAT matching network to transfer part labels from a single source image to a target. Besides natural images, diagrams often depict complex phenomena that go well beyond what a single natural image can convey. They serve as good testbeds for visual and textual reasoning. While many visual recognition tasks benefit from large-scale datasets, they are very expensive to collect, and they're not always available. We address the problem of visual understanding in the absence of large labeled datasets by treating it as a matching problem. That is, we transfer part labels from a single source to a target in 3 challenging scenarios: diagram to diagram, an image to image, and the cross-domain scenario, image to diagram. This poses many challenges. Images may lack rich textures. Some pairs may exhibit severe pose variations. Matching should be generalizable, but training with saxophone pairs makes matching in cicada pairs very difficult. Finally, the part location could be very close to each other, confusing the matching. To overcome the challenges, we propose a structured SAT matching networks, or SSMN for short. For a given source as target image pair and the corresponding part locations, we first compute part embeddings by CNNs and appearance similarity scores with context via LSTM. We call this as an appearance matching network. And a factograph is constructed with factors for appearance similarity and part appearance. On the nodes in the graph, we enforce SAT matching and global consistency constraint to match the set of part label while the geometric structure is preserved. The first term in the matching scoring function computes appearance similarity of source parts and target parts. This is a local appearance similarity between a part in source image and one in the target image. The second term is part appearance similarity. It captures the similarity between a part appearance in the target image and the name assigned to it. The third term is matching constraint. It enforces the target labels are matched to unique source labels. The last term is global consistency. It is composed of structural and appearance consistency and computes the similarity of the relationships between parts and source and target. To maximize the matching score by the function we just have defined, we search the solution space by using lasso, which is learning as search optimization with beam search. To showcase the inference progress, we show a source image whose parts are all labeled in the left. The right image has a target whose parts have no label, but the locations. After 2 initial matching of the parts, the probability distribution of the location of remaining part labels are shown as colored heat maps. At each stage of inference, the part which maximizes the matching score with regards to the previously labeled parts get chosen. This iterative procedure continues until all parts get labeled. In both diagram and image domains, we evaluate 3 trivial baseline and 2 state-of-the-art methods and our extension with Hungarian algorithm and our SSMN with evaluated model. Our model improves the set matching accuracy by 16.8% in diagram and 6.4% in image to the state-of-the-art matching network. Here are the qualitative results of diagram to diagram, image to image, and image to diagram matching. Please stop by our poster at B11 for any questions. Thank you.
So hello everyone, my name is David and I would like to present to you our work on self-supervised feature learning. So our main goal here was tackling tasks which are related to object geometry, such as semantic matching or key point detection. And the main research question here was how can we actually understand geometry of object categories without having access to full supervision. Now, a standard approach here might be to take features which are essentially coming from a classification task or classification network and apply them to geometry-related tasks, but this typically doesn't work very well. So basically, our main intuition behind this work is that instead if we force our network to match instead of to classify, this would produce nice features which could be useful for geometry-related tasks. So basically, the idea here is that we would take an input image, we would transform it twice using a pair of synthetic transformations. This would produce a pair of transformed images. And then we would simply pass those images through a deep network, and this would produce pixel-wise embeddings. Now what we can do is then set up a simple matching loss using the pairwise ground truth. And this matching loss will be simply optimizing the embeddings such that they adhere to the pairwise ground truth. So basically, this kind of architecture was already used before, but this was only used for data sets which were not having too much background clutter or limited viewpoint and appearance variations. In our case, the main contribution is that we essentially extend the approach for data sets with a lot of viewpoint variations, appearance variations, and a lot of background clutter. Now, one of the biggest issues with the self-supervision is that it will generate matches which are matching background pixels, and these are extremely hard to learn. And what is going to happen is that the network will essentially try to detect these features with some low-level features, and this is very harmful. So instead of that, what we propose is this probabilistic introspection mechanism, which instead of optimizing the matching loss, first expresses the probability of the loss being equal to 0. This is a function of the loss and a sigma parameter. Now the sigma parameter is corresponding to confidence and is another auxiliary prediction of our network. And it essentially allows us to ignore some of the background samples. And then we simply use the confidences within a novel probabilistic introspection loss by evaluating a negative logarithm of the predicted probabilities. So in order to visualize what was happening here, basically the confidence predictions, if we look at them and overlay them over the input images, we can see that the network was essentially learning to co-segment out the foreground, which was very desirable. And at the same time, interesting observation was that if we visualize the individual pixel-wise embedding slices, what we can see is that the network actually learns to detect key points, although it was instructed to learn to match. So this essentially shows a nice duality between learning to match and learning to detect key points. And similar results have been seen for different object categories. We have also conducted some quantitative evaluation. This was on semantic matching on PF Pascal. And what we can see here is that our method was on par with fully supervised approaches. And at the same time, it was outperforming approaches with similar amount of supervision. So to conclude, we have proposed a novel network which is using this probabilistic robust matching loss based on probabilistic introspection. And we have observed that by learning to match, we can essentially learn key points. So thank you very much for your attention.
Hi everyone, my name is Alexandre Sablerol, and today I'm going to present to you link and code, fast indexing with graphs and compact regression codes. This is joint work with Matthijs Douz and Hervé Gégou from Facebook AI Research in Paris. So the goal in indexing is to build an index system in memory that can hold a very large collection of items, such as images that are represented by high-dimensional vectors. Now, given a new item represented by a high-dimensional vector, we wish to find its nearest neighbors in a fast and accurate way. So there are mainly two families of indexing methods, graph-based methods and quantization-based methods. So graph-based methods are based on the idea that neighbors of a point are likely to be neighbors to each other. So they iteratively build and refine an approximate nearest neighbor graph. So examples include NN descent or HNSW. So these methods are very accurate, but they have a high memory cost. Quantization-based methods, on the other hand, represent a point by an element from a finite set. So examples include product quantizer, inverted multi-index, or optimized product quantizer. These methods have a low memory usage, but a lower accuracy compared to graph-based methods. So the question is, can we get the best of both worlds? A low number of comparisons and a low memory usage from the quantization-based methods. So our approach is called link and code, and it uses the graph structure of HNSW on top of quantized vector representations. And we show that we can actually refine the vector approximation using the graph structure. And this leads to state-of-the-art trade-offs between recall and speed. So given a memory budget, we can choose to use the memory to either store links in the graph, so a good graph approximation, or store bits to represent the vector, so a good vector approximation. On the plot, if you go to the left, you store a good graph approximation, and on the right, a good vector approximation. The y-axis is the accuracy that you get. So as you can see, there's a trade-off between the two, and there's an optimal point between storing a good graph approximation and a good vector approximation. So from this, our main contribution and a key idea is to use the graph structure to actually refine the vector approximation. So let's say we have a set of points. So the red point is the main point, and the blue points are its nearest neighbors. We have their quantized versions that are represented by squares. And now we will learn to regress a better vector approximation from the quantized neighbors. For this, we will learn regression weights beta. And these weights are learned by L2 regression. So we learn a codebook beta using the expectation maximization algorithm. So for the experiments, we experimented on two large-scale data sets. The first one is big ANN. It's a data set consisting of SIFT descriptors. So in these data sets, we get state-of-the-art recall at 1 while having the fastest algorithm. So the only caveat is that our algorithm needs more memory compared to competitors. And we also experimented on another data set, deep 1 billion, which consists of CNN descriptors. And on this data set, we improved the recall at 1 by a huge margin, while also having the fastest algorithm. So thanks everyone for listening to me, and you can find out more about our methods at poster B17.
Hello everyone, I'm Yichen. Today I will introduce textbook question answering under instructor guidance with memory network. This is the work done by Zheng, Li, Hangsu, Junzhu, and Bo Zhang. Our team comes from the Department of Computer Science and Technology from Tsinghua University. Unfortunately, the others didn't come here because of visa issues, so I will present this work for them. Textbook question answering is a task to choose the most proper answers by reading a multimodal context of abundant essays and images. However, most of the current methods are incapable of reasoning over the long contexts and images. And we use the TQA dataset to measure this task, which is a QA dataset proposed in 2017. The most significant characteristic is that every question has long essays as the context. We propose a hierarchical structure to solve this task. We built the contradiction entity relationship graph to extend the passage level multimodal contradictions to an assay level. The machine thus performs as an instructor to extract the assay level contradictions as the guidance. Afterwards, we exploit the memory networks to capture the information in the guidance and use the attention mechanisms to jointly reason over the global features of the multimodal input. For contradiction entity relationship graph, we use contradiction semantics to resolve the text, and we use new contradiction types to filter dependency relations. We then build the graph and using remainder dependency relations. We finally generate a guidance that is the suggested answers by graph matching. For attention-based memory networks, this module aims at combining multimodal data from the question. This module aims at combining multimodal data from the question, the textual and the visual context, and the guidance to reasoning out the most proper choice. We exploit memory to store the guidance, and we use LSTM and CNN respectively to extract essential facts from the input, and use the attention mechanisms to merge the latent features for reasoning. And the reasoning result is fed into the LSTM decoder to obtain the final answer. As for the experiments report, we observe that our method achieves significant results in accuracy in every type of questions. Our model IGMN also outperforms the newly released challenge results in both text-only and image-engaged questions. Since the method of the challenge are not published, the comparison is only for reference. And the challenge allows ensemble, but our method is a single model. If we use ensemble, we obtain 2.2% accuracy improvement than the challenge results of all the questions, which is also a significant result. The results of ablation experiments also demonstrate that both two modules in our method have very significant improvement. For more details, please visit our poster at B20. Thank you.
Hello everyone, I'm Kamran from University of Pittsburgh, and here I'm going to present our paper on supervised deep generative adversarial hashing network. Hashing is one of the fundamental problems in computer vision, and generally we can say that hash functions can be grouped as shallow or deep models. The shallow models suffer from handcrafted features and do not have enough capacity to capture the nonlinear nature of real data. And the deep models are prone to overfitting because there is no supervisory signals to learn the parameters. In this paper, we propose a novel framework for unsupervised hashing model by coupling a deep hash function and a generative adversarial network. We introduce a new objective function to have minimum entropy, uniform frequency, consistent and independent hash bits for real images, and employ adversarial and collaborative loss functions on generated data. Here you can see the architecture of our model, which is called HashGAN. HashGAN consists of a generator, a discriminator, and an encoder. Unlike the standard GAN, the input to our generator is concatenation of a binary, random binary and random uniform noises. And we applied the adversarial loss to both fake and real data. In the right side, you can see that we applied the hashing loss to real images in order to have nice property for its hash bits. And on the middle side, you can see that we applied collaborative loss on the fake data in order to learn the inverse mapping of our generative network. Our objective function has three terms: the standard adversarial loss, the hashing loss to have minimum entropy, uniform frequency, consistent and independent hash bits for real images, and finally the collaborative loss, which is actually for retrieving the binary input of the generator at the output of our encoder for the fake data. And using this, we help to regularize our model and avoid overfitting. We mainly compare our model in information retrieval tasks. Hash can outperform all of unsupervised deep and shallow hash functions with significant margin. As you can see in the table 1, it also outperforms some of the unsupervised model which have supervised pre-training. We also evaluate the performance of Hashcan in clustering tasks. Hashcan provides state-of-the-art results. And you can see here the visualization of Hashcan on MNIST query sets. And as you can see, it's almost discriminative representation. And at the bottom figure, you can see that the precision recall curve on CVPR10 dataset for Hashcan and 5 baseline methods, which shows that Hashcan has much more better results, the black curve. Thank you.
Hi, I'm Peter Anderson, and this work is on vision and language navigation in real environments. The vision and language community has proposed a lot of interesting tasks, such as image captioning, but also including referring expression understanding, VQA, visual dialogue, movie QA, and many others. The common thread in all these works is that these tasks are passive. The agent is not allowed to move or control the camera. So to overcome this limitation, in this work, we propose a simulator for embodied visual agents based on the Matterport 3D dataset. This dataset contains densely sampled RGB and depth panoramas from 90 buildings, including homes, hotels, offices, and churches, as shown in some of these examples. To construct a simulator from this dataset, we allow the embodied agent to move through the environments by adopting positions coinciding with the location of the panoramic images, as shown in this navigation graph. At each position, the agent has continuous control over the camera, so it can look in any direction. This particular approach discretizes the agent's navigation options, similarly to a grid world, but has the advantage that the agent will always observe real natural images. So using this simulator, we propose the vision and language navigation task. Given a natural language instruction, this requires an agent to navigate through a real environment to find the goal location. Using Mechanical Turk, we collected a data set of 22,000 such navigation instructions, and we propose a clear evaluation protocol where the agent is required to stop, at which point they are evaluated and the episode is considered a success if they stop within 3 meters of the true goal location. So let's look at some examples. As you can see here, the agent is instructed to go indoors, go past the wall with holes in it, go past the large table and chairs, which you can see there, turn right and wait there. And in this case, the agent's going to be successful. So the second example illustrates some of the visual diversity in the data set. You can see here some unusual objects and clutter, including a paddle, some nets, and fish mounted on the wall. So because the simulator is based on real environments, rarely do two objects ever look the same, and the visual diversity is much larger than simulators based on synthetic data. In this data set, the validation and test instructions are situated in previously unseen building environments. This makes the task particularly challenging, so as instructions may refer to objects that are previously unseen, such as these examples of hieroglyphs and other things. So given these challenges, a baseline sequence-to-sequence agent shown in orange, performs reasonably well in environments it's seen before, but poorly in unseen test environments. In comparison, humans, shown in black, achieve a success rate of almost 90%. So vision and language navigation is a challenging and important problem with many practical applications. To encourage further work, we provide a test server and a leaderboard. In summary, we propose the first benchmark data set for natural language navigation in real buildings. Code, model, and data is available. Please come to Poster C4 to discuss it further.
Good morning, ladies and gentlemen. My name is Maoke Yang. I'm from DeepMotion, an autonomous driving startup from China. Today, I will present our work on semantic segmentation for street scenes, which is a basic task in autonomous driving. The key idea of segmentation is to arrange suitable features for each pixel. I will propose to use dense SPP to provide base feature. Dense SPP can be seen as an improved version of ASPP in Deep Lab, and is a simple yet effective structure to bring better feature representation for segmentation, especially segmentation in street scenes. Here we show 3 typical street scenes from 3 public benchmarks. We can see large-scale variation, especially caused by perspective transformation, where near objects are large, where far objects are small. Scale variation poses challenges to segmentation since pixel-level classification requires object-level information. The similar work of ASPP in Deep Lab and PSPNet concat multiple scale features in parallel to handle scale variation problem. However, their scale range is not large enough and not dense enough comparing with object scale variations. In this work, we propose dense SPP, which densely connects multiple dilated convolutional layers. And as this picture shows, the dilation rate of each layer in dense SPP is arranged in an array manner. In our understanding, this structure has several benefits. Put a layer with more dilation rate before a layer with large dilation rate can bring denser pixel sampling. Stack several dilated layers together can significantly increase the scale range, while the dense connection brings more dense scale sampling in the large scale range. On validation set of size gaps, dense SPP improves ASPP baseline by 4.2%, measured by mean IOU, and more improvement is achieved by adding an extreme dilated layer before existing dilated layers. Equipped with strong backbones, our method is competitive with other state-of-the-art methods on test sets of size gaps. Here we show the effect of dense SPP by quantitative results, where segmentation results by gradually removing dilated layers are shown and compared. Results on large objects such as truck and wall are severely affected by removing more dilation layers. To check the possibility of running dense SPP on embedding devices, we also add dense SPP to lightweight backbone networks such as QuestNet and MobileNet. Results show that even the total model is greatly compacted, the results are still relatively good. Thanks for your attention. This is the context of our company. Thanks.
So this concludes the spotlight session. Let's thank all the speakers again.